Hello everyone, I'm Kwon from KAIST. Today I'm going to talk about tensor casting co-designing algorithm architecture for personalized recommendation training. This work is done with my colleague Yunjae and Professor Minsoo. First, let me introduce the research scope of this work. It is well known that deep neural networks are both compute and memory intensive. As such, we have seen a lot of processor architectures focusing on these dense compute-intensive DNN layers, achieving high efficiency improvement. Unlike these prior work focusing on accelerating dense DNNs, our research focuses on personalized recommendation models. For these models, sparse embedding layers incur key performance bottlenecks due to their high memory capacity and bandwidth demands. More concretely, embedding layers consist of two key primitives, embedding vector getters followed by vector reductions. As embedding getter operation is conducted over a large embedding table, typically sized as several tens to hundreds of gigabytes, both embedding getters and reduction exhibit high memory intensity, the throughput of which is bottlenecked by the memory system's performance. To address the challenges of these sparse embedding layers, our research group has previously proposed a near-memory processing architecture that could effectively accelerate the inference path of DNN-based recommendation models. Before we talk about recommendation models training, let me briefly introduce what this work is about, as it is closely related to this paper. The key to our approach is to augment the buffer device within a DIMM module with a lightweight near-memory processing core specialized for conducting vector getters and reductions. We call this tensor DIMMs, and because the near-memory processing units are stationed locally within the DIMM module, the memory throughput-intensive embedding layers can entirely be conducted locally within the DIMM device. Unlike conventional memory systems, whose effective throughput of embedding operations are bottlenecked by the interface between the processor and the DIMM modules, Tensor DIMM can drastically improve both latency and throughput of embeddings as all the key primitives are conducted near memory. Utilizing these tensor DIMMs as basic building blocks, our final proposition is to aggregate multiples of tensor DIMMs as a pooled memory architecture, which allows the several hundreds of gigabytes of embedding tables to be stationed entirely within the pooled memory node. The pooled memory architecture, augmented with our near-memory processing units, is integrated inside a high-bandwidth system interconnection fabric such as NVLinks, assuming a GPU-centric AI system architecture. Such system architecture enables the acceleration of both dense DNN layers and the sparse embedding layers for the inference process of recommendation. So, through this research, the question we wanted to answer was, could near-memory processing architectures be equally effective for training recommendation systems as well? Before focusing on training recommendation models, let's quickly discuss what are some of the general principles in designing machine learning accelerators for training. Training accelerators should provide high throughput while supporting various kinds of operations for both forward and backward propagation. To satisfy both efficiency and flexibility requirements, it is important to choose which operation should be accelerated by the hardware. If we choose to implement a specialized hardware module for each compute primitive, it will lose flexibility and hardware utilization. Contrary, if we design hardware like a CPU to support flexible operation, it will be hard to achieve the required throughput. So, it is important to find out the key compute primitive that can cover most of the target operations while enabling accelerated computing. Looking at existing AI accelerators, you will notice that most of these accelerators are optimized for a single compute primitive, general purpose matrix multiplication, GEM in short. This is because GEM operation is able to cover a significant majority of important DNN primitives such as fully connected, recurrent, and convolutions for both forward and backward propagation of these dense DNNs. Of course, converting into a GEM-compatible operation might not be free and require additional latency overhead. For instance, when converting a convolution operation into a GEM operation, you need to go through the image-to-column function, which adds performance overhead. However, the benefits of having a unified microarchitecture greatly outweigh these drawbacks. This is because having a single operator be the target of acceleration allows the underlying microarchitecture to be tuned and optimized for that one operation, which enables sustainable improvement of the microarchitecture. So the question we try to answer in this work is, for training sparse embedding layers, which compute primitive should be the target for hardware acceleration? To get there, let me walk you through the basic training process of sparse embedding layers. The training process of DNN-based recommendation model could be roughly divided into three stages: embedding forward propagation, DNN layers forward and backward propagation, and the embedding backward propagation. In the embedding forward stage, the gather-reduce operation is performed. In the given example, we are assuming a batch size of 2. Using an index array as an input, it gathers corresponding embedding vectors from the embedding table and conducts a reduction operation. Then, using the reduced tensor as an input, the DNN layers are processed for both forward and backward propagation. Once the backpropagation of the DNN layer is finished, a gradient is generated in the identical shape of the gather-reduced tensor generated during the embedding forward propagation stage. Using this gradient, the final step is to update the embedding vector locations within the embedding table that have been previously gathered and reduced during forward propagation. Since the vector addition operation was performed during the gather-reduce step, and the addition operation works as a gradient distributor during backpropagation, the gradient expand operation becomes the backpropagation operation of the gather-reduce. Once the gradients have been expanded, we go through a gradient coalescing process, which is a unique compute primitive conducted in the sparse embedding layers training. Because of the batched execution of the sparse embedding layer, some embedding vectors could be accessed multiple times within a single iteration. This means that there could be multiple numbers of gradient vectors to account for the same embedding vector entry. The gradient coalesce operation is a stage that reduces these gradients into a coalesced sparse tensor format, which contains no more than one gradient value for the same location. As we will soon discuss, identifying such coalescible gradient vectors requires non-negligible computational overhead because it entails sorting all the target indices of the expanded gradients. Once the gradients are coalesced, embedding vector parameters are updated through a scatter operation, the value to scatter update of which is generated using the coalesced gradient and the optimization function. Notice that unlike the DNN layers, which are accelerated using high-throughput GPUs or TPUs, all the aforementioned embedding primitives are conducted over the CPU because of the large memory capacity requirements of embedding tables, causing a significant performance bottleneck. The question is how much? In this slide, we show the profiling results of our studied recommendation models. We explore 4 different configurations categorized into embedding-intensive and DNN-intensive cases. Here the y-axis shows the latency breakdown of each step in the end-to-end training process. Coalesce stage is separated into 2 parts, the sorting step for finding duplicate indices and the actual coalescing of gradients. In this profiling result, we make some interesting observations. First, the DNN execution stage only takes a small fraction of the end-to-end training time even for DNN-intensive models, implying that most of the training time is spent on the embedding layer. Second, the backward propagation of the embedding layer requires multiple steps of memory bandwidth intensive operations, taking on average 80% of the end-to-end training latency. Third, while our TensorDIM-style near-memory processing solution can help alleviate the performance overhead of embedding layers, the forward propagation stage only accounts for a small fraction of end-to-end training, so it cannot help address the bottlenecks of embedding layers backward propagation. So let's come back to our original question. How should we go about designing a hardware accelerator for training sparse embedding layers? Given the memory-intensive nature of gradient expand and gradient coalesce operations, one obvious approach is to design a dedicated near-memory processing core for each of these primitives within the DIM module, similar to our TensorDIM architecture. Following the design principles of existing dense AI accelerators, which is optimized for a single primitive that is general-purpose matrix multiplication, the key to our approach is to devise a unified microarchitecture that can encompass all the major compute primitives of training embedding layers. A key observation we make in this paper is that both gradient expand and coalesce operations, the two most performance limiting primitives of embedding backpropagation, can all be transformed or casted into a vector gather reduce operation. In other words, through our tensor casting algorithm, practically all major primitives of embedding training can be executed as a vector gather reduce, which enables a unified microarchitecture design for sparse embedding accelerator. Here, I will walk you through the key intuition behind our tensor casting algorithm. An important motivation behind tensor casting is that coalescing gradients is functionally equivalent to conducting a reduction among the gradients targeted for coalescing. If we were to think of the backpropagated gradient vectors as a table storing the gradients subject for coalescing, a gradient expand coalesce operation is nothing more than gathering the necessary gradient vectors from the gradient table, all of which are subsequently reduced. Of course, to gather the necessary gradient vectors from this gradient table, you need to be able to index the appropriate set of source and destination gradients from the backpropagated gradients to the coalesced gradient. Our proposed tensor casting algorithm enables this by generating the appropriate set of casted index array such that the two-step gradient expand and gradient coalesce can be merged into a single gradient gather reduce. This slide illustrates an example set of procedures undertaken to generate the casted index array. Due to timing constraints, I will not go over the details of how this algorithm itself works. Please refer to the paper for detailed explanation. There are, however, two important points I would like to make here. First, the tensor casting algorithm is a highly throughput-bound operation, which is amenable for GPU acceleration thanks to the high compute and memory throughput GPUs provide. Second, the input index array using during the embedding forward propagation is the only input required for the tensor casting algorithm, which enables the derivation of the casted index array to be pre-computed during the forward propagation stage, hiding its latency overhead. We do this by copying the original index array from CPU to GPU so that the GPU can generate the casted index array in high throughput fashion. Because the utilization of such casted index array is during the backpropagation of embeddings, the latency overhead of tensor casting is effectively hidden. Additionally, as all the key primitives of embedding layers, embedding gather reduce, and gradient expand coalesce are now all able to be executed using gather reduce, our TensorDIM style near memory processing cores optimized for vector gather reduce can seamlessly be used for end-to-end training time reductions or thanks to the high throughput near memory processing. So, putting everything together, our final proposition is to architect a hybrid sparse dense AI system for training recommendation models. Our proposed AI system employs two types of accelerators: a sparse accelerator for training embeddings and a dense accelerator for training DNNs, all of which are interconnected over high bandwidth system interconnects such as NVLinks or CXL. When it comes to the dense DNN accelerator, the system architect can choose any commercially available machine learning accelerator optimized for training DNNs to flexibly compose the overall system architecture. For the sparse accelerator that handles embeddings, we employ a pooled memory node design similar to the previously discussed TensorDIM-based disaggregated memory system, all of which are augmented with near-memory processing units specialized for vector gather reductions. Now, I will explain our evaluation methodology. To quantitatively evaluate our proposed sparse-dense AI system, we inherit the software emulation methodology from our prior TensorDIM study, which uses the GPU cores to emulate the behavior of NMP cores, while the local GPU memory system emulates the accelerator's local memory channels. Using NVIDIA DGX-1V machine, we programmed one GPU to emulate the behavior of the near-memory processing-based sparse accelerator, while using another GPU as a dense accelerator. Our software prototype was implemented using low-level PyTorch C++ API for embedding layers. For DNN layers, we use NVIDIA cuDNN and cuBLAS library. To implement the tensor casting algorithm, we use NVIDIA Thrust and NVLab's CUP libraries. We implemented 4 different configurations of Facebook's DLRM model on top of our software prototype. RM1 to 3 follow configurations from prior work from Facebook. For a conservative evaluation, we also added another configuration named RM4, which employs an extremely large DNN layer, which shifts the bottleneck more to DNNs rather than embeddings. Using our software prototype, we explored 3 system design points. The first one is the baseline CPU-GPU system, which has the same execution flow as a current PyTorch or TensorFlow framework. The second design point is tensor-casted CPU, which uses the tensor casting algorithm to fuse the two-step expand coalesce process into a single gather reduce. It is worth pointing out that although the tensor-casted CPU is a purely software-based solution, it can still achieve non-negligible speedup thanks to the reduction in memory bandwidth requirement. The last design point is our memory-centric tensor-casted near-memory processing architecture, which employs near-memory processing-based sparse accelerator device. So here are the results. The x-axis shows the 3 design points we just discussed, each of which is evaluated over different batch sizes of 1, 2, and 4,000. On the y-axis, we show a latency breakdown of embedding forward, DNN, embedding backward, and casting overhead. As shown in this chart, our software-only tensor-casted CPU significantly reduces the latency in conducting backpropagation of embedding layers for both embedding-intensive and DNN-intensive configurations. Using our proposed NMP acceleration, our proposal achieves an additional 1.3 to 6.1 times speedup even compared to the tensor-casted CPU. So overall, for the end-to-end training performance, tensor-casted CPU achieves 1.2 to 1.6 times speedup, and tensor-casted NMP achieves 2 to 15 times speedup to the baseline. To conclude, we have proposed tensor casting, an algorithm architecture co-design for training personalized recommendation models. To the best of our knowledge, this is the first architectural solution tackling the training part of recommendation models. Using our novel tensor casting algorithm, we are able to unify all the major primitives of embedding layer training into a single vector gather-reduce operation, enabling the development of unified microarchitecture that help accelerate sparse embedding layer training, achieving 2 to 15 times speedup compared to state-of-the-art.